it's going to be fairly elementary. So the story started when, the pandemic started, and, everybody wanted to do something about the pandemic, say something about it, contribute in some positive way. And, initially I didn't know what to do because I didn't want to start studying epidemiology because, let's leave it to the experts. Let them do the publishing and write articles because, somebody like me, if I'm going to start writing about it, that's just probably going to be creating noise, right? And then I saw this wonderful article by Harry Stevens in the Washington Post. And what he did was he was using hardball simulations to explain how a pandemic spreads and how preventive measures can actually, help in subsiding it or controlling it or actually saving lives. And it was a very, very nice article. And, when I looked at those, and the best thing about the article is the animations in it, right? So I looked at those animations and I realized that I could make them and I could perhaps make them more elaborate. If he spent a week on it, I could spend a lot more time and do something more interesting. So that's what I did. And so let me share some of those animations with you. Actually, you can go and I think in the email, Rizwan has given you links. And then you can see the entire video that I made. But let me show you a little bit of it. And then we will talk about how these animations are made. And then I'm going to talk about now I have a new algorithm that I think can actually help us a lot in producing even better animations. All right. So let me share my screen. How do you share your screen? You stop the video and you say that. Okay. So is my Rizwan, is my screen shared? Rizwan?
We can see it. We can see it. Yeah.
Okay. All right. So here, this is a colliding dot animation. So each dot is representing an individual. And, the gray dots are people who are susceptible, who are not infected, but can get infected. The yellow dots are people who are infected, but they're not showing any symptoms. So these are asymptomatic people. And the red dots are people who are symptomatic. They're infected and they're symptomatic. And the green ones are the ones who have recovered. Okay. And in this, of course, we make the simplifying assumption that once you have recovered, you become immune. You can, do away with that assumption if you want. That's just doing a little bit of programming. And in this particular one, if you look closely, there's some double dots. Okay, some dots with a little circle around them. And those are the people who are practicing social distancing. And this particular animation actually was showing that how you can control the curve, right? How you can bring down the peak if if say 25% people practice social distancing. So, if you show an animation without these double circles, where everybody is not not doing any social distancing versus 25% are, you can see the two different curves and how, social distancing can help. All right. So this is an animation, and this part is not colliding dots. This part is just showing what is called an infection tree, how the infection spread. Okay. So that's one. And here, this part is actually showing how you actually compute the R value. If you know the infection tree, you can compute the R value. So that's one. And let's stop that. Okay. And let me show you one more, a couple more, and then we'll go on. So we pause this, we make this small, we close this. Did I close? All right. Play this. Let's go back to Zoom. Yeah, Zoom. And what do? Is I stop video and I share my screen. Okay, Rizwan, can you guys see the Rizwan, can you guys see the animation?
We got it.
Okay, all right. So this is a particular animation in which at the center there is a place where people can have a large gathering, right? And you know, there are two parts of the animation. In one where they don't have a large gathering, and this one they do have a large gathering. All right. And then once again, you can look at the curve and you can see how having a large gathering actually creates a very quick peak in the curve. So, you know, this animation was explaining why we should avoid large gatherings, how they can be disastrous if there's an epidemic or a pandemic going on, and how can the curve actually peak. And just avoiding large gatherings, you know, you could look at the two curves that happen, and we could also look at the infection trees and what's the distance. So that was another one. This particular one I like really a lot. So if you see now, this is when the large gathering starts. Okay, everybody sort of gathers in this stadium or something like that. Okay.
We have a question. Imran, please go ahead.
Yeah.
Yeah, Sarmad, I think the video was showing the other way around, the first video.
Here is where the large gathering happens. Right?
Here it is a large gathering. Okay. In the first one, everything was going better, getting better.
Well, that was the last part of it. So, once everybody is infected, all you have is things get better, right? Because people have become immune. Okay. So this particular animation I really like very much. I call it the MSB animation, which stands for morons spread the virus. Okay. So this okay. So let's stop this and let me show you one more. So I'm a little not very good at technology. All right. Let's get rid of this. Here's one. And go back. Okay. Okay. Okay, how do I do? Now I go to Zoom. Zoom. Okay, Rizwan, can you see this one?
We see this and we can also see your video, so no need to stop sharing. Lovely.
Oh, okay, all right, okay. So the thing is that this particular one was actually, let me rewind it a little bit. I've just gone a little over, but let me explain to you what's going on in this particular one. So in this, the little bars that you're seeing are what I call infectables. So you can think of them as doorknobs, okay? Or, you know, things that people touch. So you do have infections that can spread, not through human contact, but a human touching a doorknob and then somebody else touching that doorknob. And in this animation, you'd see that these doorknobs get yellow and orange, which means they get more and more infected, but then they're cleaned periodically, all right? So what you can do is you can change this variable of cleaning the doorknobs or not doing it, all right? And then you can compare the two curves, all right? And what you realize is that if you clean things regularly, if you disinfect things regularly, then once again, you can subside the peak. Okay, once again, you can help, you can save lives, right? So this was the point of this animation. And let's wait and see the tree that we get. All right. And what you see is, okay, it will happen now. So if you see, it's not a tree anymore, it's a forest. All right. So it's, because there are people who didn't get infected and didn't get the infection from another person, but they got it from, a doorknob or something like that. Okay. So this was the, this was the, all right, what can you see now? There should be no animation and I should be the only person there. Is that true, Rizwan? Hello?
Yes, Sarmad, we can only see you. Reading
Okay.
red.
All right, so great. So now I'm going to explain how these animations are made. Now, it's very, very simple. So what you have is two particles, right? And each particle is actually going to be given by a position, let's say pi, a velocity vi, okay? And then you're going to have a mass and a radius, okay? So these four things actually describe a hardball, all right? And if you want, you can have MIRI, you can have balls of different sizes, but let's keep it simple like that. And then you have another particle, QI, all right, and which has a velocity, let's say WI, well, let's call this PJ, okay, which has velocity PJ, and let's say the same radius R, right? Now, so this guy has certain velocity, yeah, and this guy has certain velocity. Now, the first thing what you want to do is you want to figure out whether these particles collide, and if they do, at what time. All right, and that's actually fairly simple, because if you look at the velocity of the ith particle at time t, it's just simply going to be its velocity at time 0, right? Plus t time, its position at time 0 plus
Sarmad, can you just give me 1 second? Guys, if you just pin Sarmad's video where he's, then you'll be able to see him writing on the board. You just need to pin his video. Yeah, select his video. You'll see 2 of Sarmad's videos coming. Sarmad, do you need to show any more animations?
No.
Then just stop sharing and it'll make it simpler for everybody. Otherwise, otherwise you can just pin his video and then you can see it.
I've got that. Is it okay now? Is it all right now?
Yeah, I mean, it was okay for me for me even before, but now I think everybody should be able to see you.
Okay, all right, okay. So the velocity of the ith particle at time t is the velocity at time 0 plus t times the velocity. Sorry, position at time t is position at time 0 plus t times the velocity, and the jth particle, the same equation, Vj of 0 plus t times Vj. And these particles collide if their positions, all right, if the distance of their position is 2 times r, right, because that's collision, right? These are the centers, and the distance between the centers is 2 times r, all right? And it's better to write this equation like this, all right? And then you can solve this equation and you actually get a quadratic equation, all right? And then you calculate the discriminant. If it's negative, then you get complex solutions. That means the particles miss each other. Otherwise, if you get a positive solution, then that's when the collision happens. All right, and you can work out the details of this. In fact, I think it's a nice exercise in a mechanics course to give to undergrads. and most of them should be able to do it. All right. So what happens is from this data, you can actually calculate the time at which these two particles collide, and this time is a positive number, positive real number. Okay, then the particles collide. Otherwise, we can just put infinity there, which means they don't collide. You know, if the solution is complex or something like that. All right. Now, how do we? So this is only for two particles. So now, how do we do hardball simulation? And the answer is actually we use some technology. Okay. All right. So in the simulation, you have hundreds of particles. So, you know, the system, you know, has several particles, right? Moving in different directions at different velocities, right? So for the moment, let's ignore the boundary, right? So what I can do is I can write down all particles. Let's say I have n particles in rows, and I can write down the n particles in columns. Okay, and for each one of them, all right, I calculate the time at which they collide. This is J, and this is R, right? And of course, the diagonal entries are absolutely useless. This is a symmetric matrix because if I collides with J at time Dij, then J collides with I at time Dij also. So it's a symmetric matrix. So you need to store only a part of it, but that's besides the point. This is order n squared calculations, right? Okay, so, and these Dijs are absolutely useless, right? They have no meaning in the sense that two particles may not collide. I mean, a particle, you know, these two guys may be on the collision course, but something else may come here and disturb it, right? So most of these numbers are absolutely useless. But there is one of them, okay, which is very, very useful, which is the minimum. Okay, so the first collision that happens is very important. It must happen in the real system. It must happen, you know, in the real system. The rest of the numbers are not meaningful. Okay, so let's find out that minimum. Okay, so let's call this EJ, and let's call this okay. In fact, I can color code this. Let's make PI green. All right, and let's make PJ purple. All right. So this is the first collision that happened. Okay, this is the J, which is actually the minimum. Right. Now, what you can do is you can actually simulate the system to this future time PI. Okay, you can move every particle according to its velocity, all right, and stop at PI. At that time, the purple particle would collide with the green particle. Okay. Right? Okay, so the purple particle will collide with the green particle, and let's say that they were moving like this. And all you now have to do is to update their velocities. Okay, so this was going at Vi velocity, this was going at Vj. Its velocity has to be updated to Vi prime. This velocity has to be updated to Vj prime. How do we do these updates? Well, just two things you need to know is law of conservation of momentum. and law of conservation of energy, that it's elastic collision. And once again, it's an undergrad exercise to do these updates. All right. Okay. So now we have done these updates, but now this matrix is useless, right? Because everything has changed. So we have to recompute it, but you realize that you're going to have to recompute only the row of PI, the row of PJ, the column of PI, and the column of PJ. All the other entries are not going to change. Okay, all right. So an update takes order n time. Right? So if you n particle,
excuse me, Sarmad. Sarmad, just be curious about what to do with the particle, those who are not going to collide in a finite amount of time. Then Tij will be
infinity. Yeah. So there are these infinities over here.
Yeah, thank you. And the assumption is only with the n particles which are randomly moving, right?
Yeah. The initial velocities were given. You could take them randomly. You could take them, through some other method if you want to see. If you want to see if the particles are here, what will happen, right?
Okay.
So the particles.
Okay,
yeah. Now let me explain to you these 4 edges. You can put these 4 edges here also. All right, because what might happen is like this particle is not going to hit other particles, but it's going to hit this wall. All right, and you will realize that each particle will have a finite number in one of these 4 places, right? Because it's an enclosed box, right? Therefore, the minimum is well defined. Okay, so the minimum can never be infinity. All right. Okay, so when I update this, I have to spend order n time. All right. Okay, and this is how I actually created the animation. All right. Now let me explain to you what happens when you actually do the simulation. And let's use technology. All right. So with this method, initialization is order n squared, and update per collision is order n. Okay, all right. But if you look at the collisions, let's make a timeline, right? These collisions have what is called a collision rate. They have a well-defined average that depends on the temperature and the density of the system, but it's a random process, so the collision may happen here, and then, here, and then very quickly again, and then maybe a little bit later, and then maybe 3 collisions, and then 1. Okay, so it's going to be a random, time when these collisions happen. There's going to be a well-defined collision rate. Now, when you are animating this, what you want to do is to create a frame which is faster than the average collision rate. Okay, because suppose my first frame is here and my second frame is here, so many collisions happen, you're going to see a lot of jitter, right? Okay, things collided, change their paths, it's going to be balls just bouncing around. Okay, so what you want is your collision rate to be, your frame rate to be much faster than the collision rate. Okay, so the frame rate has to be something like this. Okay. It has to be much faster, than the collision. It can happen, that Okay. So now what this means is I'm not spending order n per frame. The time that I'm spending is order n per collision. Okay, and collision rate is far less than the frame rate. Okay, so that's a very nice thing. All right, that to do this simulation, I do order n squared initialization and I do an update, and the cost per collision is linear in the number of particles. Okay, all right. So my question now is, how far can I go? How big of a system can I actually simulate using my method? All right. But there is another thing that we have to write down is the memory requirement. Okay, that's order n squared. You know, I have to actually store an array. And let me also tell you one more thing, that is how do you find the minimum in a matrix? All right. And for that, you don't need to worry. You go to an undergrad computer science student, right, who actually knows his computer science, and they will tell you about something called heaps, min heaps. All right. And in that, you can actually find the minimum in logarithmic time. Okay, so finding the minimum is not an issue. You don't have to scan the entire two-dimensional array. So finding the minimum is actually log of n squared, which is actually order logarithm, right? So finding the minimum is not an issue. Computer scientists know how to deal with it. All right. So now, in terms of time, these days I say to myself that about 10 to the 8 is what computers can deal with. All right. The computers are roughly going at gigahertz, right? And a gigahertz is roughly 10 to the 9. Okay. You can have a couple of cores or 4 cores, so you can go faster than that. But typically in an algorithm, when you write order n or order n squared, there are constants missing. So that's, you know, each step of an algorithm is not one clock cycle, but hundreds of clock cycles. So I say, okay, time is about 10 to the 8, and the same thing with memory, you know, is 10 to the 8 items we can say. Of course, our memory is in gigabytes, you know, it's 10 to the 9 something. But, you know, for example, storing a particle, you have to store the velocity, the position, and so on and so forth. And that will be several hundred bytes. So therefore, I say this is the thing. All right. So if you look at this, the highest.
Sarmad, we've lost your video. It's gone black. The screen has gone black. Could you? Yeah. I'm not sure. Maybe if you just stop the video and begin it again, maybe that works.
Okay, so it seems like my battery of the video has, of the camera has died. I have a backup battery. Okay, so just give me 1 minute, I'll fix this problem.
Please take your time.
Okay, all right. So we go to Okay, can you see my video?
Yes, we can now see it.
Okay, all right. Okay, sorry about that. I think my batteries used to last much longer, or maybe I'm taking too much time, but sorry about that. Okay, all right. So initialization is order n squared, update is order n, memory requirement is order n squared. Finding the minimum is just finding a smart computer science undergrad, so that's not an issue. So this is what I really have. So this means I can take n to be about 10 to the 4. Okay. So I can do a hardball simulation with about 10,000 particles. Okay, using this method. And the bottleneck is initialization and the memory requirement, right? So I've got to start working on these, right? Okay, now the memory requirements can be brought down a little bit, okay? In fact, memory requirements can be brought down without much thought, because what you have to do is ask yourself, well, I have this matrix, okay, and this matrix has a lot of infinities in it, which I don't want to store. You know, why store that two particles don't collide? So I only want to store the positive numbers in here. So you can ask yourself, how many positive numbers will be in this matrix, right? And of course, that's a random variable. It's not a deterministic thing, but you can convince yourself that in a hardball simulation, you know, if you have a particle, it's going to roughly, if you let it go straight and calculate the collisions, it's going to roughly hit about square root of n other particles. The other ones, it's not going to, you know, the answer is going to be infinity. All right. So it turns out that this matrix has order n, square root of n, non-zero entries with high probability. Okay, with high probability, and it's, you know, the variance is not going to be much. So if you are clever about storing this matrix, then you can bring the memory requirements down to order n squared n, right? We're still stuck in initialization. Let's not worry about that for a while, but let's see. Huh?
Excuse me, Sarmad. Sarmad, what about those particles who are colliding multiple times within a given stipulated time? So what will be the time will be assumed to put into the to become an entry of this matrix then?
Okay, so for example, let's say here's a particle, right, which is moving in this direction, and there are 4 particles or 5 particles that are, so this one is going there, so it's going to collide this one and maybe this one, right? So it will have a positive entry for this particle, positive entry for this particle, positive entry for this particle. This would be the smallest, this will be the second smallest, this will be the third smallest. If a particle is going that way, corresponding entry here would be infinity.
Okay. So you will always pick the smallest one, right?
Yeah. We always pick the smallest one and we evolve the system to that time.
So with the passage, if the two particle collides within, for instance, in the first 2 seconds, and we would like to evaluate the system after 1 hour, so we will assume a Tij for those two particles only the 2 seconds.
Yeah, 2 seconds. You'll do 2 second simulation, right? And then you'll update the matrix. Okay.
Yeah.
Because
Okay.
Those two particles' velocity has changed. Okay. And then you will take the next minimum again. Okay. And that might be 5 seconds later. Okay. And so you'll evolve the system 5 seconds and then you'll update the matrix.
Okay.
Right?
So every time we need to update the matrix in order to view. Okay. Thank you.
And see, the updating requires order and time, not square. You don't have to.
Can I just interject here for just, let's say, half a minute, going off on a, perhaps it'll be good for you to go off on the tangent and explain how silly physicists have been doing these simulations normally.
Yeah. Okay, so look, and so I'll tell you how these simulations are done. So the basic algorithm is what is called Bird's algorithm. Okay, and the way they do that is typically they will have the particles, right? Okay, and they will take a delta t, right? And they will evolve the system by delta t time. Okay, so they'll calculate where these particles will be, after a little bit of time. And then what they do is they try to do what is called collision detection. Okay, they'll see if after delta t time, which particles have collided, and they'll update their velocities. All right. So, there are, and then they do tricks with that. All right. But the thing is that in that, whatever they do, the time that they spend, and this delta t has to be taken much smaller than the collision rate. Otherwise, this doesn't work, right? Okay. And so if you think about my frame rate as being delta t, they will be, doing all these updates every time they create a new frame. All right. Whereas I only do it at when the collision happens. All right. So that's how physicists are doing it, right? But this is a slightly different method. Okay. All right.
Yeah, that's thank you. I thought it would be nice for you to just say that so that to tie in with what Imran was asking.
So the algorithm is, a collision happened, update the system to this point. Then from the matrix, find out the next minimum, which would be this. Then update the system to this point. All right. Then a collision, the next minimum would be this. Update the system to this point. All right. And updating the system means moving all the particles by, this time according to their velocities, right? And moving the two particles that have collided to that time and changing the velocity of those two particles according to the laws of physics, which is elastic collisions, right? Okay, so that's the idea. Okay, all right, so let's get back to unused technology. Right. So when I use this matrix and I use the fact that it is a sparse matrix, then the memory requirement is n square root of n. Okay, roughly that many non-infinity entries. Okay, and so this is n to the 1.5, and we want it to be 10 to the power 8. And if you calculate it, it turns out that you can take, you can take this to about 10 to the 5, 3 times 10 to the 5 or something. So that's 300,000, right? So you can actually, instead of being able to do a simulation of 10,000 things, you can maybe do it for 100,000 if you do. And your computer won't run out of memory. Initialization is going to cost you a long time. Okay. All right. Okay. The question is, can we do better? All right. And this is where I got this new idea. Okay. So, and the basic idea is that let's look at this matrix. P1, P2, and up to Pn. All right. I'm interested in the minimum quantity in this matrix, the minimum time. All right. So why am I storing the entire information? All right. So the idea is that I will go in this row and only store the minimum of the row. Okay. So what I will store is, well, this collides at 5 seconds, but I also have to store the index or the particle that it collides with. So I'll, this particle number may be P9. Okay. And I do that for the entire thing. All right. So this may collide at time 8 with particle 12. Okay. This may collide at time 6.3 with particle 19. Okay. So I get a summary of this matrix, right? What that does is it reduces my memory requirement to order n. Okay, so all of a sudden, my memory requirement goes to order n, and I should be able to do simulations with 10 to the 8 particles. Okay, that's 100 million particles. I mean, if I could do that, I'd just be, extremely happy, right? Okay, but what's the catch? All right, what's the catch? The catch is you have to twist the algorithm a little bit. All right, and let me show you what you have to do in order to accomplish this. Okay, all right. So here, the way I'm going to explain this to you is the way a graph theorist would. All right, and so I'm going to draw what is called a graph, which is a fancy name for laddu and lakiring. All right, so we have these particles. Let's say P1, okay, P2, P3, P4, P5, and P6. Bear with me, I'm just going to P7. So first I say is which particles, which is the earliest collision for particle number 1. All right, and I realize that earliest collision is with P4. So I draw an arrow, and maybe the time is 11 seconds. Right? Then I ask myself when the earliest collision happens for P2, right? And maybe this happens at, this cannot happen before 11, so this maybe happens at 12 seconds. All right. P3 hits P4 earliest. It hits other things later at time 6. P4 hits P3 at time 6. This thing hits that at time, let's say 9, this at time 4, and this at time, let's make this 8, and let's make this 9. All right. Okay. So this is the summary that I was previously saying. For each particle, so you have the time 11 and the guy that it hits, so 4, P4. For P2, you have, it hits 1, but at time 12, it hits 2, right? So this is the summary that we have, right? So from here, we calculate the minimum, it's this, right? So we have to advance our system 6 seconds, right? So when we advance our system 6 seconds, what happens is that here is, what was this, P3 and P4, okay, right? These rows have to be recalculated and their minimum has to be recalculated now, because now they have collided and they're going in different directions.
Excuse me, Sarmad. In graph theory, you are going to use not the adjacency matrices, but okay, you label the graph, and now through labeling, what technique, graph theory technique, you are using in building these matrices?
No. So what I'm doing is, this is actually my data, and I'm viewing this as a graph.
Okay. You are going other way around. Okay.
Yeah, I'm just using graph theory to help.
Yeah. I'm also interested in this part.
All right. So now I have to evolve this system to 6 seconds forward, and then P3, once it has collided. So this picture has nothing to do with what's happening with the dots. All right. So P3 collides with P4, right? And their directions change. Okay. So the data for P3 and P4 is no longer, valid, because now the collision has happened and the direction has changed. So these two entries have to be recalculated. All right. So that means I'll have to compute P3 collide time with everything and take the minimum and replace it here. All right. And P4 and its collide time with everything and take the minimum and replace it there. All right. And that's going to take order n time. Okay. All right. Okay. All right. But if you do this, you'll get a wrong algorithm. All right. And the reason is, look at P1. P1 was going to collide with P4 at time 11. Okay, but P4 has changed its direction. All right, so P1's entry is also invalid. Right, so this entry is also invalid. Okay, so you have to recompute this. All right. In fact, you will have to recompute all the entries that are pointing to either P4 or either P3. And recomputing each entry will be a penalty of order n time. Okay. All right. So, because P4 and P3 are no longer moving in the same direction as they were, not only their arrows which were going out of them are invalid, but all the arrows which were coming into them are also invalid. All right. And that begs a beautiful question. Well, let's call this a penalty for the algorithm. How many penalties do I have to accept? How many penalties on the average will I have to absorb? How many times will I be penalized if I apply this algorithm? And experiments are showing me that for low density simulations, it's order 1. Okay, so on the average 3 or 4 penalties. It's not a big deal, a few penalties. So the time becomes order n. Okay. The memory requirement goes down to order n. Okay, so now I'm hopeful that I can do a simulation of hundreds of millions of particles. Okay, so let's see now where we are. All right, so initialization. Memory, update. All right, these are the 3 things. And memory, we have gotten it down to order n. All right, and this is worst case order and not expected. The update, we have gotten it to order n, but this is expected. Or on the average. Okay. And so we should be looking at simulations of this size, but the misery of life continues. Unfortunately, the initialization is still order n squared. Okay, all right. So now, so you keep working on a problem and it's like a balloon. You capture this part and something else becomes a troubling thing, and you capture that part and something else becomes a troubling thing. So initially I didn't know how to initialize it, how to, the only way was to make the matrix, right? Or not really make it, but implicitly make it and take the minimum and then put the summary or the minimum in this thing. But even though I don't use this memory, I have to go through every single particle. So there were n squared things. So this is where we are stuck. And now I will tell you that I found a solution to this thing. Okay, all right. And let me explain this to you, and I'm not going to go into detail because I think I've taken up plenty of time, and I think question answers would probably be better. So let's do this. So if you are a computer scientist and you sort of spend your time reading things that you have no business reading, sometimes that is beneficial. Okay, so there is this subject called computational geometry, which which I am not very good at and probably never will be, but I keep reading what's going on in there once in a while. And I found this thing which is called range trees. Okay, right? And range trees is a data structure. Okay, to store two-dimensional data. Okay, so if you have particles, data points like this, right, then what you can do is you can store them in this data structure, and the storage time is order n log n. Okay, all right. And then what you can do is you can, once they've been stored, you can do something called range queries. All right. So a range query is you give it a box, an access parallel box, all right, and you say what are the points that fall in there, right? And this damn thing is going to reply the range query in order log n time. Okay, all right. So this is now how I do the initialization. I take all my initial positions and I throw them into a data structure, which is range trees. And then for every particle, I just take a window of small size, okay, find out all the points that are nearby and calculate their collision rates. All right, and that's it. Okay, so if I do this properly,
Sarmad,
huh?
excuse me, Sarmad, here n is going to be the particle which are coming in this yellow box? Or
no, n is the total number of particles.
so it will stay constant, your O and log of n, right?
Yeah, O log of n will stay constant, and so it will return you the query in that much time. And actually, it can give you a summary of what is inside this range. So, for example,
okay,
you can say which is the fastest particle, or what is the average speed, or whatever. So there are many range queries you can do. Okay, all right. But if you store this initially using this technique and do that, well, the initialization time okay, goes down to order n log n. Okay, and log is a very slowly growing function, right? So you could think of log. So log of a billion is what, 30. Okay, so you could, well, initialization is going to take you 30 times more time than update. That's okay. You can wait. You can say, my update is happening every 1 second. For initialization, I have to wait 30, 35 seconds, 40 seconds. So what that allows you is, now I think this allows me to actually think of doing, hardball simulations with 100 million points. Okay, and that would be very satisfying. Okay, now here's the funny thing, that I haven't really gone around and looked a lot at literature at what is going on. Okay, I've just been having fun with this myself. Okay, so, and Rizwan said, why don't you present this? Hopefully that will get me a little more organized, and, maybe I'll write it up, and so that's it. Let's start here.
Great. Thank you very much, Sarmad, for a lovely talk. We are now open for questions. I already see Jam Sadik wanted to ask something. He just typed a question in. Jam, could you just speak it out?
I have few remarks, Sarmad. It is for the first time I am listening to you, and I heard a lot about you. Yeah, and I think the expectations, जितना मुझे पता लगा था वो कम था, but you are really a good illustrator and very good in explaining ideas. I really enjoyed the talk and the technique, and I really love it. Just one question, Sarmad. In this particular model, you fix the volume of, or in other words, this is a planar sort of model.
You could do this in 3 dimensions. The mathematics, the programming and the mathematics doesn't get harder.
Okay, and in fact, the main thing is that there was one problem. Probably you can put your hand on to that particular thing. I don't know. Did you came across the infinite billiard ball problem, which Mariam Mirza Khani did work on?
The
infinite billiard ball. I am going to.
Oh. Yes. I'm aware of Mariam's work. Okay.
And
look, Mariam is so versatile, and she has done work in such. Some of her work is very difficult, but I've only read 2 or 3 papers by her, and 2 of them have to do with graph theory, and the other have to do with matrix theory. This particular one, I know she's very famous for it, but maybe the mathematics is beyond me.
नहीं सरमद, ये जो infinite pool table वाला problem है ना, infinite pool table mean के there is a table, billiard ball table, and there the table is frictionless, and you put throw the particles, and particles are colliding with each other, and you return to the table after a billion years or so time. So what will be the case? And this is a real life phenomena, the movement of the celestial objects. So sometimes they are rotating around each other, but in complete mathematical point of view, your initial discussion of the model reminds me that particular thing. Me and Amir, we had a long discussion on it, and this is you can relate your work with that, and probably you can.
Well, one thing that you can do is, if you know that problem better than me, I'd love for you to come and meet me and teach me. Okay, because that's, I think, the best thing is कि मुझे कुछ आता है और वो मैं आपको सिखा दूँ, आपको जो आता है वो आप मुझे सिखा दें. So, and then I would go ahead and look at it.
I during the talk, I was just overlapping your technique with the technique what they used, and there was a lot of similarity in the sense you did your indigenous work. Definitely, you find out thing and fit in a very nicer way. And the only part, particularly that would be very interesting, is the computational geometry. So you went with the range tree, and they come up with okay, the particles are moving, so what about the convex hull is changing with the movement, and with the convex hull movement they sorted out the problem, maybe a different kind of problem, because you were using a different type of scenario, and they were handling the infinite pool table where the balls are moving.
So I would like to say just one thing about the range trees, right? The range trees have 3 operations that they support. One is insertion of particles, the other is deletion of particles, and the fourth is the range query, right? Now, in my problem, I neither need insertions nor I need deletions. All the particles are given initially, right? And therefore, you do not need to use something called range trees. You can use a simpler data structure, which is called range arrays. Okay? Structurally, it is like range trees, but it's much easier to implement, and it takes a lot less memory. Okay? Lot less memory, I don't mean, means you can save constant amount of a constant fraction of the memory. All right. So it would also take n log n memory, but the constants would be very small. So that's an aside you can also do.
I really love it. Thank you, Sarmad.
Okay. Yeah. Once again, I really liked, you guys are very kind and nice, but let's just forget that it was a good lecture. Okay, let's talk mathematics.
Yeah, I love
feel
it.
very ashamed,
No. In fact, it is not
Okay.
something, because
Could we-
I like your style of explaining things. I really love it.
Okay,
Thank
could we move on to the next question, please? Aurangzeb has his hands up. Please go ahead, Aurangzeb.
Yes, please. Actually, Sarmad, hello, how are you? So
Hi.
there is no question, definitely another great lecture. But I would say that you are not that bad with technology. It got revealed finally by your handling of camera. That's all, but just a note. Have fun, take care.
Look, I have created wonderful technology. Have you seen an eraser like this? This is. Thank you. Thank you.
Asif, you have Abdullah. Are you still around? Abdullah, you had a question from the talk. Abdullah, are you around? Is Abdullah still around?
Yes, sir.
Okay.
Please go ahead and ask your question, Abdullah.
My question was, when we initially saw the simulations, we saw that we were recognizing that each particle would be a person, and that we determined them to be either infected, to be recovered, or immune. And so my question was that if we say that we have a person, and that if you say that this person is wearing a mask, what does that do for the simulation? Will the size of the particle just reduce, or are we going to add like a probabilistic factor? Okay, if two particles do collide.
Yeah, very good question. Very good question. So the way I had done the simulation is I said that the people who are not wearing a mask, let's say, they are just circles, and the people who are wearing a mask are double circles like this. Okay, all right. And so if I take initial positions and I rerun the system, the physics is not going to change, because this outer circle is not really, it's not really mass there. Okay, when the collision actually happened between the double circle, it also happens like this. This is just indicating that they're wearing a mask. So the physics doesn't change, right? But what I do is I change the probability of the infection getting passed. So in this particular animation, here the probability was half, and for these one, it was 1/4. Okay. So if you rerun the animation, the physics is not going to change. Exactly the same collisions are going to happen. All right. But the epidemiology changes, because the infection moves slowly, and therefore the peak goes down. Yeah. So if you really want to do these simulation for epidemiological purposes, what I do is first I do the physics. Okay. And the physics tells me which particle collides with which other particle at what time. All right. And then there is another program that just does the epidemiology. What does a collision mean? Whether the person was infected, whether they were wearing a mask, or things like that. Right. Does that answer your question?
Yes, it does. Thank you.
Okay.
Rinku, please go ahead.
Sarmad, I had a question regarding the people who say get infected and were to die. Would your simulation, the thing you said about the balls could get deleted, you could use that parameter that they could get deleted by taking in what's the percentage of people who are dying, and then delete some balls accordingly, and your simulation could incorporate mortalities?
Yes. That's a very, very nice question. And of course, showing death and actually is, by the way, there's a higher species that is interrupting me. So I'll tend to the higher species and come back. Go, go. Okay, sorry about that. Okay, so dealing with death, what I could do, for example, is the dot that has gone red, right, which is showing symptoms, with certain probability to change their color to black, okay, and logically remove them from the system, right, so that nobody is colliding with them, okay, and then we can count the black dots and we can put that in our graph. All right, so there are two reasons people don't do that. You know, Harry Stevens doesn't do that in his article. Epidemiologists don't do that in their article. And there are two reasons. One is death is a very sad thing. And, you know, by not showing that, we are hoping that an epidemic, you know, nobody will have to die. You know, that we are hoping that we'll be able to save everybody. Okay, so that's the first reason, that you know, you don't want a YouTube video in, you know, which maybe young people will watch, and, you know, they will have to think about death. You know, maybe a 6-year-old may watch this video, right? And, you know, they will have to think about that. So there's this humanistic reason why we avoid that. The second reason is that it doesn't really matter. So, you know, in the SIR model, there are people who are susceptible, infected, and you can have recovered/dead. Okay. Now the recovered people do not spread the infection, and the dead people don't either. Okay. So actually, by introducing R/D, you don't gain anything in the SIR model. So they say, well, you know, if you don't gain anything, you know, let's just lump these people in the same category. You know, it's either you're dead or you're recovered. You know, either way, your contribution to the model is going to be the same, right? So by adding that category, you don't gain much. All right. I think if you really want to do these simulations seriously, by looking at the curve, right, or by looking at all the people who were infected, you can look at the death rate and just multiply it by that and get that number that you want, if you want that. So those are the two reasons. Is that now people may not agree with me. People may say, look, we need to face reality, show deaths. And I think they have a valid point. I wouldn't say they're completely wrong. It's just we disagree on, I disagree with those people and I'll take my choice. Right? Does that answer?
Yeah, I understand your point about being sensitive when in the times of pandemic, and not making it accessible for all age groups. However, in a research community, perhaps a select group of people can see what is actually the state of the pandemic in terms of mortality and compare it with, say, SARS or Ebola and other pandemics, and look at what is the mortality profile of COVID-19.
Yes, you're absolutely right. As far as serious research is concerned, you would want to refine this model far more, right? Because we have children, right? And there the mortality rate is very low. Then we have old people where the mortality rate is very high. And from what we understand is children are not, you know, they don't get symptoms, but they are spreaders, you know. They get COVID from their parents, and then they go to schools, and you know they give it to another child who goes back and gives to his or her parents or grandparents. So if you really want to do research level, research community, you will have to refine this model a lot. Okay, and it can be done. You know, it's not. I don't think so. Getting a very refined model is a is a matter of years. You know, I think 5-6 smart people can sit and take my programs and perhaps come up with a very reasonable model. But the problem is I don't know what the cutting edge community is doing, you know. So my
Maybe
purpose,
you need a student, Sarmad.
well, my purpose is purely pedagogical, okay, in the sense because I'm not an epidemiologist, I don't want to disturb that community at this moment. Let them do
Well,
their
you
work.
could help. Maths would definitely help understand what is the mortality profile. That's what I feel, but I leave it at that.
Okay, yeah, that's good.
We do happen to have another couple of questions. Hamir, can you go ahead? And once Hamir is done, then Dharmender, you can ask your question, please.
Hello, Sarmad, and nice to see you, and a very nice lecture. I had a follow-up to Rinku's question. So I could think of another reason why you wouldn't want to do this. And that reason is not moral, but technological, in the sense that you would couple the physics with the epidemiology of the simulation. And that would introduce, let's say, a backward feedback into the physics simulation where particles are disappearing. And this could be harder to do on, let's say, a technological level as well, harder to implement in a sense. Because your particles would be disappearing after you did the probability calculations. So it wouldn't be a strict layering model.
Yeah, so what you're saying is that it would make the programming more difficult or developing the algorithm more difficult?
It would make the programming more difficult, yes. Both of those things.
Yeah, but see, the thing is, Hamid, that is both, that's a sword that cuts both ways, right? So if the programming is more difficult, you can try to avoid it, or you can say, oh, here, I have another challenge, right? So it depends on how you think about it. So we'll have to think about what deletion would do to the entire program. You're right. And that can be, you know, irritant, and it can also be a joy, right? Because you have created a new problem. So.
And the second part is, have you looked at, let's say, simulations where deletion does occur? And do they have the same, let's say, overall probabilistic characteristics as when it does not occur? So,
okay, so as far as the literature surveys are concerned, I'm not an expert in it, and I haven't seen, I haven't done a very thorough literature survey. The thing is, as far as simulations are concerned, for simulating n particles, physicists are not really interested in hardball simulations. Okay, they are interested. So, for example, if you take n particles and these are stars and you want to simulate a galaxy, right? Then, as particles come closer, the gravity increases, right? And so, and when, you know, say two stars are about to collide, you know, something strange happens. It's not a hardball collision, right? Or even when they take, you know, subatomic models, when particles come very close to each other, their behavior changes, right? Okay, you know, quantum effects come in and all that. So hardball simulation, I think, is mildly interesting or moderately interesting for physicists. Other kinds of simulations are more interesting for them, and that's why I think the BIRDS algorithm survives, because it allows you to do more sophisticated simulations.
okay. My question was more from the point of, does, for example, the death ratio change, or does, for example, the spread of the disease change if you have taken into account, let's say, the disappearing balls?
I will answer that question. So epidemiologists study, they do not do these colliding dot simulations, right? They write down differential equations, right? So there's the SIR model, okay? All right. And this SIR model is susceptible, infected, and recovered. There are no dead people. And then the model is actually a differential equation, right? It's well known that in this SIR model, introducing death doesn't change the predictability. All right. Okay. This is the most fundamental model. And then they have several other models, right? Because some diseases SIR is just too simplistic. For example, for COVID, I'm not using SIR, I'm using asymptomatic infected, symptomatic infected, and R, right? So that's a slightly more. So these are models that are based on different equations, right? The model that I am studying is not based on a differential equation. It's based on, let's call it colliding dots. Colliding dots. Okay. Now, there is a theorem whose formal proof still I haven't written down, and I think I can prove that, which is that in the limit, and limit taken properly, the colliding dot simulation actually becomes the SIR model. Okay, all right. And you would want to prove this kind of theorem, because what you would want to do is you would want to say that your model at least approximates the model used by professional epidemiologists. Okay. So does that answer the question?
Yes, that more or less answers my question. So if in the limit it doesn't change anything, I don't think adding.
Yeah.
You could just take, for example, the simple ratio and calculate, for example, the removed.
Yeah. Look, there's a lot of. So I am a theoretical computer scientist, and so I'm not very good at doing experiments and collecting data. But there's a lot of work one can do around this. So if I find a good student who can work on this, that would be nice. Okay.
Dharmendra, please go ahead.
Huh?
Hi, Sarmad.
Yeah.
सर मेरा क्वेश्चन ये था कि ये जो अब मैट्रिक्स बनेगा इसका ऑर्डर क्या होगा, और जो अपडेटेड मैट्रिक्स होगा उसका सेम ही ऑर्डर रहेगा या?
Order mean it's an n by n matrix, so it's an order n squared entries in the matrix. और जो updated
ठीक, अपडेटेड मैट्रिक्स का भी ऑर्डर सेम ही रहेगा?
हाँ. So yeah, you have this matrix, right? And the easiest way to think about it is the yellow, and here's the yellow particle, and here's the purple particle, and here's the purple particle. These are the particles that collide, and you have to update the yellow row, yellow column, purple row, purple column. Yeah. So order
सर, और सर आपने जो प्रोग्रामिंग लैंग्वेज यूज की है वो इसमें मैटलैब सही नहीं रहेगी क्योंकि मैट्रिक्स है यहाँ पे?
So the thing is that I am extremely lazy at learning programming languages. So I used to do C++, and now I do Python. So it's hardly a problem. Oh, by the way, when I started hitting barriers, जब मेरी calculations बहुत time लेती थी, तो मुझे पता चला कि Python बहुत slow है. ठीक है ना? तो फिर मैंने हमीर से कांटेक्ट किया, because Hamir is an expert on NumPy, okay, which is a very fast library for doing numerical stuff on Python. So after having a long discussion, I asked him, would it be better if I program this little part in C? And he said, oh, that's the best solution. So, I'll just use the language that I'm convenient with, because it's so much. Yeah, I've never used MATLAB, so why would I want to spend my time learning it?
Okay, sir. Thank you.
Yeah, MATLAB is not going to help you. I know from experience, it's going to be slower.
Okay.
Right. All right, if somebody wants to ask a question, they can just speak up right now. Otherwise, I don't see any other questions and we can thank the speaker. So let me count down from 5. 5, 4, 3, 2, 1. Thank you, Sarmad. Lovely talk. Lovely to have you. And
Thank
we'll meet soon.
Okay, thank you all. Thank all of you for listening to me patiently, and it was very nice. So goodbye. Okay, thank you.